A-Level Chemistry, Paper 3, 2018. Question number 1. Probably the hardest question on the paper, and it caused a lot of problems. So we've got iodide ions reacting with hydrogen peroxide ions and reacting with H plus ions. The rate equals the rate constant multiplied by the concentration of hydrogen peroxide multiplied by the concentration of iodide ions to the power 2 multiplied by the concentration of H plus to the power 2. So a large excess of H2O9 minus is used so that the rate of reaction is only affected by H plus. How can that be? Well, what actually happens is if you use large excesses of these hydrogen peroxide and iodide ions, then any changes in concentration to these are negligible and so will have no effect on the rate. The easiest way of explaining that would be if, say for example, I poured a cup of salt into the sea, it would have a negligible effect on the concentration of salt in the salt water. That's because the sea is so large. So changing the concentration of these is going to have a negligible effect because you're using a large excess of them. And now I want to measure, it says that you're going to titrate with alkali to determine the concentration of H+. What must be done to the sample before it's titrated? Well, you need to stop it reacting. So you've got to stop it reacting so you can determine the H+ concentration at that point that you've taken the sample. So the best way is to stop the reaction maybe by cooling it or maybe by adding some water to dilute it so that it stops reacting. You get a straight line on this graph. So if you had a curve, you'd take a tangent to the curve and you measure the gradient. We've got a straight line, we haven't got a curve, so the gradient is staying the same throughout, it's remaining constant. Now the gradient is the rate, so the rate is staying constant, so you've got a constant gradient as the H+ changes, and therefore the rate isn't changing. So that means that the order with respect to H+ is 0. Changing the concentration of H+ has no effect on the rate. So the rate equals the rate constant, because if the H+ concentration is having no effect on the rate, and the other chemicals, the hydrogen peroxide and iodide, are in large excess and they're not affecting the rate, then the rate constant equals the rate. Yeah? So the gradient equals the rate constant. So we take the value of y, 0.5, we divide by the value of x, which is 420, and it comes out as 0.0012. What are the units? Well, the moles per decimeter cubed divided by seconds, so that works out as moles per decimeter cubed, mole dm to the minus 3 divided by s, so that's s to the minus 1. Question 1.5, you've got a similar experiment and you've got some results now, time versus H+, and you've got to plot them on the graph. So there's marks for plotting them on the graph and drawing a line of best fit, which is a curve. Calculate the rate of reaction when H+ is 0.35. So at 0.35 H+ concentration, you've got to draw a tangent to the curve, and then depending on how far you go, you measure the y-axis, so the change in y divided by the change in x. My values give 0.18 divided by 440, but it would depend on how far you extend the line and how big you make the triangle. You may want to go right to the axes at the far end so that you can read them from the x and y axes, but it should work out at 4.09 times 10 to the minus 4, or similar. You'll be allowed a small amount out from that. Question 1.8. You've got a reaction with A, B and C as reactants and it's making D and E is blue, it's a dark blue colour. So the reactants will go blue straight away as E is made. However, you can add a reagent X, and what X does, it reacts with E. And so as it reacts with E, then there won't be any blue colour. But when X runs out, then E is produced and the blue colour appears. So whilst X is still not fully used up, then E won't be produced and it won't be blue. It's only when X runs out that E will appear. So what we're going to do is we're going to try and determine the order of reaction with respect to A. So we're going to have to change the concentration of A and see how that affects the reaction. The amounts of B and C, the volumes of B and C, and the concentrations of B and C will stay the same. And we're going to use a fixed amount of X to keep the reaction fair, to keep the experiment fair. So first of all, we're going to have to measure out a set volume of A, a set volume of B, and a set volume of C in separate containers. Yeah, we'll measure out a volume of X into a separate container as well. So I've got a certain amount of A, a certain amount of B, a certain amount of C, and a certain amount of X in separate containers, in separate beakers, let's say. It doesn't matter how much you have. Next, we're going to put X into the reaction mixture. It says that you put X in first. A small amount of X is included in the initial reaction mixture, so X will go in first, and then maybe you'll add A and B and start the reaction by adding the third chemical C. So you add X, which is the reagent which is going to react with E, and A and B, and you can start the reaction by adding the third chemical C, and you're going to start a timer, a stopwatch, and then you time how long it takes for X to be used up, or rather for the E to start appearing and the blue colour appears. Then you repeat it with different volumes of A, and from that experiment then we can work out the initial rate of the reaction. So what's going to be fair each time? We've said already the total volume. So the total amounts, even though we're varying A, will make up the remainder with water, so that the concentration of A changes, but the amounts of B and C are the same. So we'll keep the amount of B and C the same, and the concentrations of B and C the same by using the same amounts each time. And we'll vary the amount of A, but we'll change the concentration of A by making it up to the same volume each time. We'll have to use the same temperature as well, so temperature doesn't affect the reaction. And then what we're going to do is we're going to plot a value of 1 against time against the concentrations of A. That's fairly standard for working out for a plot of from a rate equation. Order from the shape of the graph will tell you what kind of order with respect to A that's going to be. If it's a straight line, it'll be first order. If it's a curve, it'll be second order. Question 2 is about the element sodium to sulfur in period 3, reacting with oxygen to form oxides. Give the equation for sodium reacting in oxygen. So Na plus O2 is going to form Na2O. How do I know that it's Na2O? Well, sodium's in group 1, so we'll form 1 plus as it loses 1 electron. Oxygen's in group 6, so we'll gain 2 electrons, 2 minuses. So I'm going to need 2 Na pluses to balance with the 1 O2 minus. So Na2O, and then I'm going to need 2 in front of the Na2O to balance the 2 oxygens, and therefore I'm going to need 4 Na. Observation, so it will burn with a yellow flame, and this sodium oxide is going to be a white solid. A white solid because it's not a transition metal, it's not got an incomplete 3D orbital, so it's a white solid. Phosphorus, so this time you've got to know the formula of phosphorus oxide as P4O10, and therefore you need 4 P's and 5 O's to balance. Observation, again, a white solid. Or you could say burns with a white flame, either of those will do. Explain the increase in melting point from sodium oxide to magnesium oxide. Well, Na is in group 1, sodium's in group 1. These are ionic solids, so it'll form Na plus. Magnesium will be Mg2 plus, so sodium 1 plus, Mg2 plus, so magnesium is more ionic, and so it'll have a greater charge, stronger ionic bonding in Mg2 plus to the O2 minus, because Mg2 plus has got a larger charge. Explain why the melting point of the oxide of silicon is much higher than that of phosphorus for 3 marks. Well, silicon oxide forms a giant macromolecular structure, whereas phosphorus is a small molecular structure. So a giant covalent or macromolecular structure, a bit like diamond or graphite. P4O10 is molecular, so once you've got 4 P's and O10s, it doesn't get any larger than that. Those are a single molecules then that are attracted to each other by van der Waals forces, whereas SiO2 is a giant covalent macromolecule with covalent bonds between all of the atoms in a large lattice. And so the bonds in SiO2 are much stronger than the intermolecular weak van der Waals forces in P4O10. The sample of the highest oxide of phosphorus was prepared in the lab. Describe the method for determining melting point. So you put a small amount in a melting point tube, and then you melt it. You heat it slowly at first. Well, you can say heat it slowly throughout, actually. You heat it slowly, especially near the melting point, the expected melting point. And then if the melting point agrees with the data book value, you know you've got a pure sample. It also melts sharply if it's pure as well. Question 3. We've got cyclohexene can be prepared by the dehydration of cyclohexanol using concentrated phosphoric acid. You usually use concentrated sulfuric acid, but in this case they've used concentrated phosphoric acid. It'll do the same thing. Prepared cyclohexene by placing 10 centimeter cubed cyclohexanol density 0.96 into a round bottom flask. So we could use density equals mass over volume. Here we've got the density, we've got the volume. We could work out therefore the mass of cyclohexene that we've got. Phosphoric acid added to the flask. Student added anti-bumping granules before heating to prevent large bubbles forming. Student heated the mixture, distilled off the cyclohexene. The distillate was poured into a separating funnel and washed by shaking with sodium carbonate. Presumably that's to remove any of the phosphoric acid that's remaining. Sodium carbonate reacts with acids. Periodically the separating funnel was inverted and the tap opened, presumably because we're getting sodium carbonate makes bubbles of carbon dioxide with an acid. So sodium carbonate can be used to test for acids. It makes carbon dioxide, so separating funnel was inverted and tap open, presumably to release the pressure. The aqueous layer was discarded and the final organic product was dried using anhydrous calcium chloride. That's a solid that doesn't dissolve. It's an insoluble solid and it'll absorb water, so it remains as lumps basically in there, and it will absorb any water. After the product was dried, the drying reagent was removed using filtration, so you can remove it because it doesn't dissolve under reduced pressure. So you use a Buchner funnel and a side arm connected to the tap, so reduced pressure or vacuum filtration. Calculate the percentage yield of cyclohexene. So we've got the amount of cyclohexene that we've made. Originally we've got density equals mass over volume for the cyclohexanol. So we know 10 centimeter cubed, density 0.96. So we've got cyclohexanol, density is mass over volume. We've been given the density, we've been given the volume. Density is in grams per centimetre cubed, so we leave the volume in centimetre cubed when we do density as mass over volume. Mass is 0.96 times 10, 9.6 grams of cyclohexanol. We can work out the MR of cyclohexanol, and we can work out the number of moles of cyclohexanol, because moles is mass divided by MR, 9.6 divided by 100. I've got 0.096 moles of cyclohexanol. Now, 1 mole of cyclohexanol makes 1 mole of cyclohexene, so 0.96 moles of cyclohexanol should make 0.96 moles of cyclohexene if I get 100% yield. So I've got 0.096 moles of cyclohexene. The MR of cyclohexene I can work out as 82, so the moles of cyclohexene, moles is mass divided by MR, so 0.096 moles equals mass divided by 82. 82 multiplied by 0.96 tells me that I should make 7.87 grams of cyclohexene. I make 5.97 moles of cyclohexene, so I divide 5.97 by 7.87 and it will give me 76%. They're allowing somewhere between 75.8 and 76%. Describe test-tube reaction on the product to show that cyclohexanol had been dehydrated. Well, it's making cyclohexene, so the test for a double bond is bromine water. Would go from orange to colourless. Suggest why sodium carbonate was used to wash the distillate. That's to remove any acid left in the flask, so we're using phosphoric acid, so it'll remove any acid. Explain why it's important to open the tap of the separating funnel. So the sodium carbonate and the acid are going to make bubbles of carbon dioxide. You need to release that. Give a property of anhydrous calcium chloride other than its ability to absorb water that makes it suitable as a drying reagent. It remains as a solid, it doesn't dissolve, so it remains as a solid, so once it's absorbed any water in the mixture, it can be filtered off. Describe the apparatus used to remove this drying agent. Well, you use a special funnel called a Buchner Funnel, and you use a side-arm flask or a Buchner flask connected to the tap for vacuum filtration or reduced pressure filtration. So a Buchner funnel, you can actually call it a flat bottom funnel as well, but its real name is a Buchner funnel, containing some filter paper, of course. And the Buchner flask underneath, or a side-arm flask, is connected to the tap to a vacuum pump. A sample of cyclohexene had been contaminated with cyclohexanol. The cyclohexene can be separated from cyclohexanol by column chromatography. Silica gel is used as the stationary phase and hexane as the mobile phase. So silica gel will stay in place, and any polar molecules will adhere to that, will be retained by that and stick to it essentially. Any non-polar molecules will move more quickly past the stationary phase, and hexane is the mobile phase that will be used to rise up the column, or run down the column rather. Column chromatography runs from top down to bottom, unlike paper chromatography that runs from bottom to top, and that will pull the cyclohexene through the column. Explain why cyclohexene has a shorter retention time. A shorter retention time means it's going to run through the column more quickly than cyclohexanol. It's because cyclohexanol has got an oxygen to hydrogen, a very, very polar bond. So the polar bond is going to adhere or be retained on the silica gel. So cyclohexene is non-polar, cyclohexanol is polar. It's going to have hydrogen bonds, so the cyclohexanol has, you could say, greater affinity, attraction, retention to the stationary phase. It's basically going to stick to the stationary phase and not move as far or as quickly as the cyclohexene, which is non-polar. Explain how an infrared spectrum would confirm that cyclohexene obtained from the chromatography column did not contain any cyclohexanol. Then you've got to look in your data book, and you'll find there's no peak at 3230 to 3550, which would indicate the presence of an OH bond or an alkyl, an ol. Question 4. A student carried out an experiment to find the temperature rise for a reaction between hydrochloric acid and sodium hydroxide. Used a measuring cylinder to place 50 centimetre cube of 0.4 mole decimetre cubed hydrochloric acid into a glass beaker. So if we wanted to, we could find out the number of grams there, we could find out the mass by using, we could work out the number of moles and the mass. So moles equals concentration equals moles divided by volume, and then we could use the MR to work out the mass of hydrochloric acid if we needed to. The student recorded the temperature at 1 minute intervals for 3 minutes. At the 4th minute, they mixed the chemicals together and started to mix the solutions, didn't record the temperature. So we're going to have to extrapolate this line forward, and we're going to have to draw all these and extrapolate it back. So draw it back, draw this one forward, draw this one back, look where it crosses the point at 4 minutes and measure the temperature change. Because we haven't got the temperature change at the 4th minute when we started mixing, we have to draw these lines forward and draw it back, a process called extrapolation. The student recorded the temperature at 1 minute intervals for a further 8 minutes. Fine, the results are shown, so we're going to have to draw it. Plot a graph of temperature up the side against time along the bottom. Use your graph to find the temperature rise at the 4th minute. Shows your working. So we've got the temperature up the y-axis using sensible scales. So we've got the temperature along the y-axis here going up the side, and we've got the time along the bottom. And then at the 4th minute, we're going to have to plot all the points correctly, but all the points correctly on the graph. 2 lines are best fit, so one going forward and one coming backwards. Extrapolate to the 4th minute, so draw a line up from the 4th minute and see where the first line crosses and where the second line coming backwards crosses, and then measure the temperature change. And the temperature change should be around 2.1 degrees C if you've done that correctly. The uncertainty of each temperature, the key word here is each temperature reading, so you're measuring the temperature twice. For the thermometer using the experiment was 0.1. So you've got a temperature change of 2.1, but you've taken the temperature readings twice. So we need 2 times 0.1 because the uncertainty each time is 0.1, and we're taking 2 readings. So 0.2, 2 times 0.1 for the 2 readings. 0.2 out, it could be 0.2 plus or minus 0.2 out from the real value, divided by the temperature change, which is 2.1, multiplied by 100%. We've got a 9.5% uncertainty. Suggest to change the experiment and minimise heat loss, then you'd use an insulated cup or an insulated beaker, or maybe put a lid on it to reduce heat loss. Suggest and explain another change to the temperature that increased the percentage uncertainty in the use of the same thermometer. Well, look at the temperature change. It's only 2.1. So as you get a larger temperature change here, a larger temperature change, 0.2 divided by a larger number will give you a lower percentage reading. In the same as if you do a titration, if you use a small volume from your burette, you get a high percentage error, so you dilute your solutions in your burette. In this case, I want a larger temperature change, and so to get a larger temperature change, I'm going to increase the concentrations of my chemicals to try and increase the temperature change, increase the size of the temperature change, because if I get larger than 2.1 here, the larger this value, 0.2 divided by a larger value is going to give me a smaller percentage error. And you can do that by increasing the concentrations of the chemicals that you're using. Second student completed an experiment to determine the enthalpy of neutralization. So you've got an acid and a base, or an acid and an alkali reacting together. The reaction between ethane dioic acid, where it's got 2 carboxylic acid groups, and potassium hydroxide. The student added 25 centimeters cubed of 0.8 mole decimeter cubed ethane dioic acid. So that means that we've got a volume and a concentration. We can work out number of moles. To 75 centimeters cubed of 0.6 mole decimeter cubed of potassium hydroxide. Again, we've got a volume and a concentration. We can work out number of moles. We've been given a temperature increase, so maybe we're using Q equals minus MC delta T. Given equation for the reaction between ethane dioic acid solution and potassium hydroxide. So I've got this here. You maybe remember ethanoic acid and sodium hydroxide makes sodium ethanoate, CH3COOH and NaOH makes CH3COO, Na and water. So we've got the same kind of thing here. So but we've got 2 carboxylic acid groups, and so we need 2 potassium hydroxides to make 2 waters. So the hydroxide part reacts with the acid part, so the OH part reacts with the H of the carboxylic acid and makes water, and the potassium reacts where the H has been, so you get COOK, and at this end you'll get COOK. So same kind of reaction, as I say, between ethanoic acid and sodium hydroxide to make water and sodium ethanoate, but we've got potassium instead of sodium, and we've got 2 carboxylic acid groups at either end. Okay, let's have a look at the next bit then. So for the calculation, well, first of all, before I sort of go into this part of the calculation, I know why I've been given a volume and a concentration of ethane dioic acid and a volume and a concentration of potassium hydroxide. That's to work out moles, so let's do that. Concentration moles divided by volume, so for the ethane dioic acid, concentration 0.8 equals moles divided by 0.025 moles, multiply the 2 together to get 0.02. Same for the potassium hydroxide, concentration 0.6 equals moles divided by the volume 0.075, moles is 0.6 times 0.075, 0.045. Just remember you're not using centimetre cubed, you're converting centimetre cubed into decimetre cubed, smaller unit into a larger unit like a decimetre cubed, then you divide by 1000, and that's why I've used 0.025. I've converted the 25 centimetres cubed by dividing by 1000 into decimetre cubed, and similarly for the 75 centimetre cubed I've divided by 1000 to get 0.075. So that's where those two numbers have come from. Okay, the next bit then, I know that if I've been given a temperature change, and more importantly I've been given a specific heat capacity, the only equation that I know with specific heat capacity is Q equals M minus MC delta T, or delta H equals minus MC delta T. What's the mass? Well, the mass is the volume of the liquid. I've used 25 centimetre cubed and 75 centimetre cubed. So I've used 100 centimetre cubed of solution, and it says assume the density of the reaction mixture is 1 gram. So 1 centimetre cubed is 1 gram. I've got 100 centimetre cubed. I've got 100 grams of liquid. Remember, it's the liquid. This equation refers to the amount of liquid that you have that you're heating up. Specific heat capacity 4.2, temperature change 3.2, minus 1344, and it's in joules. So that's my heat change. Potassium hydroxide is in excess. Ethane dioic acid is the limiting reactant. What I mean is that there's plenty of potassium hydroxide. The reaction stops and that amount of heat is given out when the ethane dioic acid is used up. Because look, there's only 0.02 moles of ethane dioic acid. There's more potassium hydroxide. So ethane dioic acid is the limiting reactant. Even if I use 1 mole of this with 2 moles of potassium hydroxide, as seen in the first bit of the equation, this doubled is 0.4, this is 0.45, so I've got an excess of potassium hydroxide. It's this using up. When this gets used up, then the reaction stops and that amount of heat is given out. So we've got to work it out now. I've got minus 13344 joules of energy been released exothermic minus when I've used 0.002 moles of ethane dioic acid. The question is, how much, calculate the enthalpy change per mole of water. Well, first of all, I'm going to do it per mole of ethane dioic acid. How much would 1 mole of ethane dioic acid give out? So what I've got to do is I've got to work out what I multiply by. So I do 1 divided by 0.02, which means I've got to multiply by 50. Those slightly stronger at maths will just multiply 1 divided by 0.02 by this value here. But I'm scaling up by 50 times. Minus 1344 times 50 is minus 67200 joules. That's how much energy is given out when 1 mole of ethane dioic acid is used. Now the question says how much per mole of water formed. So let's have a look back in the equation. 1 mole of ethane dioic acid makes 2 moles of water formed. So I've worked out how much energy is given out when I use 1 mole of ethane dioic acid. It's asking me how much per 1 mole of water. So I'm making 2 moles of water. 1 mole of ethane dioic acid makes 2 moles of water. How much energy will be given out if I only made 1 mole of water? I've clearly got to half this. I've got to divide this by 2. So if I divide minus 67200 joules by 2, I end up with 33,600 joules. It's asked me to work it out. It's not actually asked me to work it out in kilojoules, but if I were to work it out in kilojoules, then I'd divide by 1000. You usually have the value in kilojoules per mole, minus 33.6, but it hasn't specified for me to put it in kilojoules per mole, so minus 33600 joules will get you the mark. In a similar experiment, the enthalpy of neutralization for the reaction between sulfuric acid and potassium hydroxide was found to be minus 57.0 kilojoules per mole. So, in other words, sulfuric acid and potassium hydroxide is more exothermic, minus 57 kilojoules per mole instead of minus 33.6 kilojoules per mole. Why is that? So, sulfuric acid is a strong acid. It's fully dissociated. So, it's fully broken up into H pluses. There's no sulfuric acid, it actually breaks up fully into H pluses. So being a strong acid, therefore you're going to get a more exothermic reaction because you've not got to use any of the energy to dissociate the acid. So less energy is needed to dissociate the sulfuric acid. So I'm not going to need any energy in actual fact to dissociate the sulfuric acid. It's already fully dissociated. So whereas with the ethane dioic acid, then here, because it's not fully dissociated, you're going to need to use some of the energy that's released to actually dissociate that ethane dioic acid. So your answer to get the marks for the 2 marks for this is all you need to write is sulfuric acid is a strong acid, so less energy needed to dissociate the sulfuric acid. The rest of it sort of explains really what I've just been talking about. Question 5. Which can be both an empirical and molecular formula of a stable compound? I can probably do this by elimination actually and then work out the correct answer. P4O10, well that's not an empirical formula because it could be simplified to P2O5. NH2, well you can have NH3 but not NH2. NH2 nitrogen has 3 bonds because it's in group 5 of the periodic table and wants to gain 3 electrons, so it'll have 3 covalent bonds like NH3. It won't have 2. CH3 carbon has 4 bonds, not 3, so CH3 isn't correct. CH2O is correct, so you could have carbon to oxygen double bond and 2 hydrogens. That would be methanal. Question number 6. Which diagram shows the correct bonding and correct polarity in a molecule of oxygen difluoride? Well, we can do some elimination first of all. Fluorine is in group 7, highly electronegative, more electronegative than oxygen. Fluorine is highly electronegative, only wants to gain 1 electron, very small, so would pull that in close to its nucleus. So they're going to have delta minuses, and the oxygen would have a slight delta plus, because fluorine is more electronegative than oxygen. So clearly it's either A or C. What would actually happen? Well, fluorine wants to gain an electron, it's in group 7, and oxygen wants to gain 2 electrons, hence 2 covalent bonds, because it's in group 6. And so they'll both put an electron into the share, so A is correct. C shows that there's some kind of dative or coordinate bond here with fluorine donating the pair of electrons into the covalent bond. Now they both want to gain electrons, so we'll put an electron each into the bond. A is correct. In the early 20th century, the apparatus shown the diagram was used to investigate atomic structure. When He2 plus particles were fired at a thin sheet of gold, most of the particles detect at point P. In other words, they pass through a gold sheet. What conclusion can be drawn? I think most gold atoms are mainly empty space, so they're not being deflected by the atoms in the gold sheet. However, a small number appeared at point Q, so there was some reflection back. So there must be something in the gold sheet repelling those electrons to send them back again. So these +2 particles must be repelled by something in the gold sheet. Not many of them come back, so it's mostly empty space, but a few do come back to point Q. So 1 in 8,000 particles must be repelled by something positive charged. A very small part of the gold sheet must be positively charged. So gold atoms have a small positive nucleus. A is your answer. Question 9. Which equation represents a termination step? So immediately it's D, because you have to have 2 radicals coming together in a termination step. And on the left hand side, A, B and C don't have 2 radicals coming together as 2 reactants. So your answer is D. Question 10. Which is correct about the molecules shown below? I know D is definitely correct. Potassium cyanide in a nucleophilic substitution reaction. I know Cn- uses a lone pair on a carbon to react with aldehydes. It will react with the delta plus on that C, electrons will move onto the O, and that will form O minus, and a lone pair of electrons on the O will then react with H plus, because this KCN will be in something like acid or methanol. So I know D is definitely correct, so I know D is the answer. Let's work out why A, B and C are not correct. It reacts with HBr in an electrophilic substitution reaction. No, it's electrophilic addition across a double bond. It reacts with NABr in a nucleophilic addition elimination reaction. Now you get addition elimination reactions when you have acyl chlorides with COCl, not aldehydes. It reacts with ethanolic potassium hydroxide in an elimination reaction. It would have to have something to release. So say, for example, in an elimination reaction, it's with something like a haloalkane, where it might attack an H, and then the H would move the electrons into a bond and release maybe the Br. I suppose it's possible KOH in an elimination reaction, the OH takes an H off there and the electrons go into here. No, the Br isn't adjacent to the CH3. So if the OH minus attacked that H and took that off as H2O, the electrons from the CH would go into this bond here. So the C would have to be adjacent to a Br, so that C there would have to have a Br. No, C is incorrect. D is your answer. Which statement is correct about both 2-methyl-butan-1-ol and 2-methyl-butan-2-ol? So I've drawn 2-methyl-butan-1-ol and 2-methyl-butan-2-ol. They can both be formed by the hydrolysis of esters. That's possible. An ester, COOH, could be broken by hydrolysis, adding water back in to break up the ester back into a carboxylic acid and an alcohol. Alkaline or acid can catalyze the hydrolysis, the addition of water back into an ester to create the carboxylic acid and the alcohol, so that's possible. They can both be oxidized by a reaction with potassium dichromate. Well, that would form a ketone there. Well, it can't do that, so you can't oxidize a tertiary alcohol, because if that carbon formed a ketone, that carbon would have 5 bonds. Both be formed by the hydration of methyl-butyene. Let's think about methyl-butyene. Butyene, it's got a double bond between carbons number 2 and 3. So the hydration is adding an H and an OH. Now the OH could go into carbon number 2 or carbon number 3. If the H and the OH added across the double bond, it would never form the OH. So if the double bond were here in methyl-butyene, so if it was CH3CCH3 with a double bond here, the OH could go onto carbon number 2, or it could go onto carbon number 3 when you dehydrate it with an H and an OH, so that if there's a double bond there, the H could go on here and the OH here, or the H here and the OH here, but at no point would the OH appear on carbon number 1. They both have 4 peaks in their carbon NMR spectra. No, with that methyl group being offset, we're going to have 1, 2, 3, 4, 5 peaks in this one, and with that being offset, 5 peaks in each. Now your answer is A. Solutions of 2 compounds W and X react together in the presence of a soluble catalyst Y as shown in the equation. When the concentrations of W, X and Y are all doubled, multiplied by 2 that is, the reaction increases by a factor of 4, increases 4 times. Which is a possible rate equation? Well, if W doubled, multiplied by 2, 2 2's are 4, and X doubled to twice as large, that would increase 4 times, that would increase 2 times, that would increase by 8, not by 4. Again, this one would increase by 4 times, that would increase by twice. 4 times 2 is 8 times. Oh, this one looks good. C, if that doubles and that doubles, so times is by 2, times by 2, 2 2's are 4. C would work for me. What's wrong with D? I've got Z, which is a product. So Z as a product wouldn't feature, it's reactants that feature in your rate equation. Question 13. In a series of experiments to find out the order of reaction with respect to reactant X, which graph would show the reaction is second order with respect to X? Well, the graphs don't come down, they go up, so as you increase the concentration of X, the rate's going to increase. The question is, does it increase proportionately or does it increase on a curve? First order reaction is, overall first order reaction is a straight line, a curve is second order, so your answer is D. Which equation represents the process that occurs when the standard enthalpy of atomization of iodine is measured? Standard enthalpy is at room temperature, so at 25 degrees C. So first of all, the gases are out, so iodine is a black solid, so it's either A or B. Both making gases is correct. I need to make 1 mole of atoms, so I need half I2. This is going to give double the value, making 2 moles of atoms. So the fact that I've got a solid indicates that it's in the correct state, a solid iodine, black solid at room temperature 25 degrees C, and making 1 mole of atoms. The answer is A. Which structure is formed by aspartic acid in a solution at pH 12? Well, pH 12 is basic. A base accepts H pluses, so it's going to remove H pluses from one of these chemicals. It will remove H pluses from the COOH and remove the H plus and leave COO minus. So that's correct. The problem is here that I've got another COOH here which isn't affected. So both of them will be affected, especially in such a highly basic solution as pH 12. So I'm looking for 2 COOH minuses. My answer is D. So this will remove an H plus from both of these carboxylic acid groups. How many peaks in the 13 carbon NMR spectrum of 1,4-dimethylbenzene? Let's have a look at 1,4-dimethylbenzene. Well, it's completely symmetrical, so carbon number 1, 2, 3, 4. I've got 2 methyl groups, one at carbon number 1, 2, 3, 4, 1,4-dimethylbenzene. So the thing is, it's completely symmetrical, so in terms of equivalent carbons, the carbon here, the methyl group here, the carbon in the methyl group here, and the carbon in the methyl group here are in the same environment. So that's 1. These 2 on the corner are 2. These 2 are 3. And actually these are 3 as well because it's symmetrical. So these 2 are in the same environment as these 2. So I've got the 2 methyl groups, the 2 carbons here is a second peak, and then the other 4 carbons in the ring are a third peak. The answer is C. Question 17. Which of these period 3 elements has the highest melting point? Well, we've got a mixture of metals and non-metals, so we're looking for something metallic on the left of the periodic table. So aluminium and sodium are metals, phosphorus and sulfur are towards the right, they're non-metals. So it's either between A and C as metals having strong metallic bonding, rather than something with molecular bonding like phosphorus and sulfur. Aluminium forms Al3 plus ions because it's in group 3. We'll lose 3 electrons, Al3 plus sodium, Na1 plus. So the aluminium's got a greater charge, so it's going to have stronger metallic bonding between the 3 electrons that are released when the ions formed, which are delocalized in the metallic bonds. Chlorine reacts with cold aqueous dilute sodium hydroxide, which is a complete list of the products. Well, this is something to learn, really. This is an equation you need to learn. Sodium hydroxide and chlorine makes NaCl, NaClO, and H2O. And so I've got NaCl, so it's either A, C, or D. I make water, so now we're between A and C. And so the final question is it sodium chlorate 1 or sodium chlorate 5? This is sodium chlorate. Na is always plus 1, it's in group 1. Oxygen is always minus 2, it's in group 6, gains 2 electrons. So what's missing? A plus 1. Plus 1 and minus 2 leaves no charge. So it's chlorate 1. So your answer is A. Question 19. Which products are formed when magnesium reacts with steam? Again, it's a reaction you need to know, so it's answer C. magnesium and water. So when water is a gas, it makes magnesium oxide as a white solid and hydrogen gas. Which observation would confirm that ammonia gas is released when solid ammonium chloride is warmed with solid calcium hydroxide? Well, I've got a gas, so it's going to be just above the solid, held just above the solid. It's either C or D. Turns litmus paper red or blue. Well, ammonia is a basic gas, so it's alkaline or basic. It's going to have a pH of about 10 or 11. It's going to turn litmus paper blue. Answer D. The repeating unit of a polymer is shown below. So I've got an amide link, a CONH link, sometimes also called a peptide link if it's in a protein. The CONH, and at this end I've got an NH, and at this end I've got an H. So that linkage there, that peptide link, is formed from this unit and this unit. So this one I'd have NHCH2, NH, and then this would have an NH2 on this end, and this would have been an NH2, and this would have been a carboxylic acid, COOH, or maybe a COCl. So a COOH with an NH2 would release water as a condensation reaction. A COCl, an acyl chloride group and an amine group, and NH2 would release HCl as white steamy fumes in a condensation reaction. But this has got CO, that's been, let's assume it's been a carboxylic acid group, COOH at this end, and it would be COOH at that end before it links on, and this one will be NH2, an amine group, and NH2 at this end. So I'll need two monomers, one with two carboxylic acid groups, and this one with two amine groups. So I'm not going to have one monomer, so it's automatically between C and D. It looks here as if they want me to use an acyl chloride, which is fine. So I've got an acyl chloride, COCl, would react with an amine here and make HCl as white steamy fumes when it forms this amide link. So which one is it, C or D? And I'm matching up CH2,4 here with CH2,4 here, not CH2,6. So the answer is C, that matches up with that section there. That's the monomer that will create that section of the polymer. My answer is C. The structure of part of a polyester chain is shown below. So we've got a polyester, the COO here, and we've got a long chain molecule. Which statement correctly explains why plastics made from this polyester only soften at high temperatures? Well, first of all, soften. To melt them, you're breaking the intermolecular bonds between the chains. You're not actually breaking the bonds within the chains. It's the intermolecular bonds between the chains that you're breaking to separate the chains to make it soften. So that's the first thing. Hydrogen bonds and van der Waals, so they're intermolecular bonds, forces exist between polyester chains. So for a hydrogen bond, I need an oxygen bonded to a hydrogen, a nitrogen or a fluorine. And I haven't got an oxygen bonded to a nitrogen, hydrogen or a fluorine. So I haven't got any intermolecular hydrogen bonds. Permanent dipole-dipole forces and van der Waals force exist between polyester chains. Yes, that's true, because I've got a polar bond here with my oxygen more electronegative than my carbon, so this would have a delta minus, this would have a delta plus. So I'd have a polar bond, and then I'd have in an adjacent molecule, I'd have another polar bond and have dipole-dipole attractions between the polymer chains. I'd also have van der Waals force, of course, the attraction between the electrons in one molecule and the nuclei in another molecule. I'll always have van der Waals forces as intermolecular bonds. So B is correct. Let's just check the other. The carbon-carbon bonds in the chain are strong. You're not breaking the carbon-carbon bonds within the molecule. You're breaking intermolecular bonds. The carbon-oxygen bonds in the chain are strong. No, you're not breaking bonds within the chain. You're breaking bonds within the molecule. Your answer is B. The nitration of benzene used in nitrating mixtures follows: concentrated nitric acid and concentrated sulfuric acid. Which statement is correct? This is quite tricky. HNO3 acts as a base. Well, let's have a look what's lost. From HNO3 has become NO2. So I've lost an H, I've lost an O, and if it's become plus, it's lost a minus. I've lost an OH minus, so it is acting as a base. Bases like sodium hydroxide, potassium hydroxide make OH minuses, which then accept H pluses and make water. So a base produces OH minuses, which accept H pluses. So H3O is acting as a base. Let's just check out the others then. HNO3 is acting as a catalyst. That means it's reformed on the right hand side. No, it's not. HNO3 is acting as an electrophile. An electrophile is something that bonds with a double bond, like a carbon to carbon double bond, like in electrophilic addition with HBr across a double bond, or sulfuric acid across a double bond, or Br2 across a double bond, or reacts with a benzene ring. It's not accepting any electrons from a double bond or a ring from sulfuric acid, so it's not C. HNO3 is acting as a reducing agent. Let's just check that out. Oxygens are -2, so 3 -2s are -6. A hydrogen is usually a +1. So -6 add 1 is -5, so the nitrogen must be +5. +5 + 1 is +6, and 3 -2s is -6. So that nitrogen is in +5. Here I've got two minuses. 2 minus on the oxygen times 2 is -4, and it's -4. There's 1 plus over on the right hand side. That's +5 as well. So +5 there, -4 to leave 1 plus. So it's not been oxidized or reduced at all. So it's not an oxidizing agent or reducing agent. The answer is A. Aqueous solutions of ammonia, ethylamine and phenylamine are prepared. What's the correct order for the pH values of these solutions? Well, let's have a look at something like phenylamine. So you're looking at the availability of the lone pair on the nitrogen. You could say, you wouldn't say this in an exam, but you could say, is it large or is it small? Is it a large electron pair, lone pair, or is it smaller? The larger the electron pair, or we say the more available the electron pair, that's the correct way of saying it. So the more available, or the larger the electron pair, the more likely it is to accept an H+, react with an H+, and act as a nucleophile by donating the pair of electrons and react with an H+. That's what a base does, react with an H+. So this one, a phenylamine, has got a low availability of a lone pair because the electrons here are being withdrawn into the ring. Nitrogen hasn't got any withdrawing groups or any electron repelling groups, whereas something like a CH3 or a CH2 would repel electrons, increasing the size, or as we say, increasing the availability of the lone pair of electrons to act as a nucleophile, as an electron pair donor, and accept this H+ as a base does. So let's have a look. Which is the strongest correct order of pH values of these solutions? So I'm looking at answer C, because ethylamine is the strongest base that would have the highest pH value, and then next would be ammonia, and then next would be phenylamine. So strongest base, medium strength base, weakest base. So we're looking at answer C. 25. Which element forms an ionic oxide that can react with strong alkalis? You're just going to learn this really. Aluminium is something called amphoteric. It can show acidic and alkaline properties. It can react with alkalis. Aluminium oxide is amphoteric, reacts with acids and alkalis. Metal oxides are usually basic, so they normally metal oxides like magnesium and sodium oxides are basic oxides and react with acids. Sulfur forms sulfur dioxide, so that's acidic and would react with alkalis, but it's not ionic. Sulfur dioxide is molecular, doesn't form ions. But aluminium oxide, Al3 plus O2 minus Al2O3, is amphoteric and it will react with acids and alkalis. Which statement is correct about this reaction? The coordination number of cobalt decreases. Well, you might think so from it going from 6 down to 3, but this is a bidentate ligand. It means that both of it forms 2 coordinate or dative bonds with the CO. So this bidentate ligand 2 coordinate or dative bonds from each of the 3, still has 6 coordinate or dative bonds amongst those 3 ligands. So the coordination number stays as 6 because that's a bidentate ligand. The enthalpy change is large and positive. Well, we have no evidence of that whatsoever. The entropy change is large and positive. So I've got 4 molecules forming 7, so I'm getting more disorder by making 7 molecules on the right from 3 on the left, so C is correct. The shape of the complex changes from octahedral. Now it's still octahedral, it's still got 6 dative bonds around it, even though it's got 3 ligands. They've each got 2 dative bonds from each ligand, so it's still octahedral, because that's a bidentate ligand. So your answer is C. Which complex exists as optical isomers? Might just be easiest to learn the EDTA. EDTA has 6 ligands from the 6 coordinate bonds or 6 dative bonds from the 1 ligand. So from the 1 ligand, from the 1 molecule of EDTA, it forms 6 bonds. And so in a way there's 3 different bidentate ligands, 3 around it. The same thing can happen with something like 1,2-diaminohexane, where you get 3 bidentate ligands. In this case, you've got 1 ligand with 6 different coordinate bonds. It's called hexadentate. But if you get sort of that kind of shape of 3 or 6 dative bonds from 1 ligand, this kind of shape, it can show optical isomers. So your answer is C. How many structural isomers with the molecular formula C5H10 can react with Tollans reagents? So Tollans reagent has got a CHO, and you're looking at 4 different ones. So Tollans is an aldehyde with a CHO group on it. I could have 5 in a line. I could have 4 in a line with my CHO at carbon number 2. I could have 4 in a line with my methyl group at number 3. So here I suppose you could say I've got 4 in a line there with my CHO being at carbon number 1 and my methyl group at number 2. So I've got 2-methyl-butanal. Here I've got 3-methyl-butanal. Here I've got pentanal, and here I've got 2,2-dimethyl-propanal. So your answer is 4. Which ion cannot catalyse the reaction between iodide and peroxidized sulfate? So let's have a look where iodide is here. It's been made in this reaction with an electrode potential of plus 0.54. So if it was a reactant reacting, it would start here and make iodine and 2E minus. And so if it were here going in the other direction, it would be minus 0.54. My peroxidized sulfate is going in the right direction. Here it is as a reactant, making 2SO4, 2 minuses. That's plus 201. So I'm going to add these two together, plus 201 minus 0.54. So the electrode potential for this reaction between the two is plus 201 minus 0.54 plus 1.47. Now I've got another ion which is going to catalyse it. Let's have a look at the possibilities. When I look at the reaction and add on the electrode potential for this ion, when I add it to plus 0.47, it needs to leave a positive value overall if the reaction is going to go ahead. So CO2 plus, where's CO2 plus? It's here. It's being made in this reaction. So if it's going to be a reactant, it needs to go in the other direction. And in the other direction, it's minus 1.82. Minus 1.82 plus 1.47 would give an electrode potential of a minus value, minus 0.35. So that one wouldn't go ahead. So the answer is A. Let me just check Cr2 plus. Cr2 plus is here. Cr2 plus is a minus value, but it going in the other direction, if it's a reactant going in the other direction, it's going to be plus 0.41. 1.47 plus 0.41 is 1.88. 8, so that would go ahead, it's a positive value. Fe2 plus, it's here, so going in the other direction, Fe2 plus going in the other direction, being a reactant here and forming Fe3 plus, it would be minus 0.77. So minus 0.77 add 1.47 is going to give a positive value of 0.7. And finally, Fe3 plus going in this direction is plus 0.77. Add 1.47 would give an answer of 2.34. So my answer is A. Which species has a shape influenced by the presence of one or more lone pairs of electrons around the central atom? So let's have a look which one of these have got lone pairs. Al is in group 3, so it's got 3 electrons in its outer shell, 3 Cl's bonding with 3 covalent bonds, each of those 3 electrons, one each, for each of the Cl's in a covalent bond. That's going to have no lone pairs left over. ClF3, well, Cl's in group 7, 3 F's bond to 3 of those electrons in 3 covalent bonds. That will leave 4 electrons left over. It'll have 2 lone pairs. Those 2 lone pairs will go one up and one down at 180 apart, and will leave 3 bonding pairs in a trigonal planar shape with a bond angle of 120. So that's influencing the shape. That's got lone pairs. Let's check the others out though. I is in group 7, plus lost an electron, so now got 6 electrons, got 6 F's bonding each of those 6 electrons each in 6 covalent bonds, so that will have no lone pairs. P is in group 5, gained an electron, so it's now got 6 electrons, 6 Cl's, each bonding with 6 covalent bonds. Each of those 6 electrons got no lone pairs left over. So my answer is B. Solutions were mixed using equal volumes of each solution. Which pairs of solutions would give the greatest mass of solid? Well, in this one I'm going to get barium chloride and magnesium hydroxide, barium sulfate and magnesium hydroxide, barium chloride and sodium hydroxide, and barium sulfate and sodium hydroxide. Well, for a start, barium chloride is soluble, magnesium hydroxide is insoluble, so I'm getting one soluble and one insoluble product. Here I'm getting barium sulfate, which is a white solid used in barium meals. Magnesium hydroxide is insoluble, so I'm getting barium sulfate insoluble, magnesium hydroxide insoluble. I'm getting 2 insoluble products. Sodium hydroxide is soluble, barium chloride is soluble as well, so I'm getting 2 soluble products here, and I'm getting barium sulfate, which is insoluble. I'm getting sodium hydroxide, which is soluble. So there's only B that gives 2 insoluble products. Which indicator should be used in a titration to find the concentration of a solution of methylamine using 0.01 mole decimeter hydrochloric acid? Well, 0.01, if I do minus log to the base, this is a strong acid, so I'm getting 0.01 hydrochloric acid. It completely dissociates into its ions, so it's going to make 0.01 H pluses. If I minus log to the base 10 of that, that's pH 2. So pH 2, and the shape of my curve is that it will start with pH 2, and then it will rise, it will go, and then it will rise very sharply from pH 2 upwards, and then start to tail off, because this is a weak alkali, a weak base. So I'm looking at something like pH 2 up to maybe something like pH 7, pH 8 before it starts to tail off then and slowly increase up to probably about pH 10. So I've got a shape of a curve that's going flat and then up and then tailing off slowly for a strong acid and a weak base, and it's starting off at pH 2. So this is not in the right range. These are not in the right range. It's pH 3 to pH 4.6 where I'm getting an equivalence point, where I'm getting an end point where the pH is rising quickly. So my answer is B. Question 33. Lattice enthalpy values can be obtained from Born-Haber cycles. So that's using an ionic lattice model, making an ionic lattice, and by calculations based on perfect ionic model, where atoms form perfect ions by either losing or gaining electrons. So both of these are based on ions, the perfect ionic model forming an ionic lattice. Which of these compounds shows the greatest difference from these? In other words, shows the least ionic character? Well, what about something in group 1? Something like cesium is very big right down the bottom of group 1, very large, lots of shielding. The electron, the outer electron, is far away from the nucleus, will easily form an ion. It'll have a low first ionization energy and form Cs+, lose its one electron very easily. F is very small. It's at the top of group 7, wants to gain one electron and will do so very easily because it's small. It will attract that electron close into its nucleus and will be tightly held. That electron will be pulled in, attracted into the atom to form F- very, very readily. Cesium's in there again in B. I is a large atom, so in group 7, so isn't going to form I- and attract an electron very well because it's got lots of shielding. The electron that will be attracted will be into the outer shell, far away from the nucleus. So I isn't going to show much ionic character, but cesium is. In this one, lithium is very small and in group 1, so its electron will be tightly held, so it's not likely to lose that very well because it will be tightly held. There's no shielding, so the nuclear attraction from very, very close to that energy level, being very small and close into the nucleus, that electron will be tightly held and have a high first ionization energy, so that's not going to form a very ionic compound. However, the F is very ionic. Group 7 wants to gain one electron, very close to the nucleus, being very small, will tightly pull in that electron very, very easily, will attract that electron very, very easily and hold it tightly to the nucleus. D has got worst of both worlds. Both atoms, lithium and iodide, are not going to form ionic ions very well. So lithium, being very small, isn't going to lose its electron very well. Iodide, being very large, isn't going to attract an electron very well. Lithium iodide D is the least ionic, and that's your answer. (34) For this reaction, which combination of temperature and pressure would give the greatest equilibrium yield of the product? So which of these conditions will produce most Y and most Z? So let's have a look at temperature first of all. This is an endothermic reaction. It's a positive value. So that means that in this direction, when W and X react to make Y and Z in the forward direction, this takes in energy. It's endothermic, takes in energy. Exothermics minus gives out energy. This is endothermic, takes in energy. When W and X make Y and Z, this takes in energy from its surroundings. So if I increase the temperature, high temperature, by Le Chatelier's principle, the system opposes that change, the reaction opposes that change, and it will shift in the direction to try and lower that temperature. So if I increase the temperature, make it high, Le Chatelier's principle says this reaction will shift in the direction to try and lower that temperature and oppose the change that I've just made. So it will shift to the right hand side, because in that direction it's lowering the temperature of the surroundings. It's endothermic and lowering the temperature. I increase the temperature, shifts to the right hand side, makes more Y and Z, and lowers the temperature to oppose the change I've just made. So Y and Z, more Y and Z are made in the mixture when I make it a high temperature. So I'm looking at either A or C as my answer. Next, I have got 2 moles of reactants, 1 mole of W and 1 mole of X, 2 moles of reactants, 1 and 1 make 2. In the right hand side I've got 2 moles of Y and 1 of Z, 2 and 1 make 3 moles. So I've got 2 moles of reactants and 3 moles of product. When I increase the pressure, increasing the pressure will try and lower the volume. I will try and compress these gases by increasing the pressure, and I will squeeze or compress 3 moles down into 2 to try and lower the pressure. So if I increase the pressure, 3 moles of gas will be turned into 2 moles of gas to lower the volume and reduce the pressure. So if I increase the pressure, high pressure, 3 moles of gas will be compressed into 2, and the equilibrium will shift to the left hand side. So it's not high pressure, it's low pressure. Low pressure allows the 2 moles of gas to expand into 3 moles of gas on the right hand side and make more of Y and Z. So I'll need a low pressure and a high temperature. My answer is C.